I want to start looking at the last topic in chapter 13. That's going to be tessellations. Tessellations are fun with your class. It's really creative. So a tessellation of a plane is filling the plane up with some repetition of figures so that there's no overlap and there's no gaps. This is a great one to print out copies of an animal and see if they can do this and create this. MC Escher is an excellent person to look at for examples of tessellations. Tessellations with regular polygons are more appealing to us because they're easier to create. It's easier to fill a page or a plane with a shape because we can just easily stack them up next to each other. The more irregular our shapes get, so if they're not congruent on all sides, the more difficult it is to actually create the tessellation. So when we say regular polygons, we're talking about polygons that have all the same length for every side. So, which regular polygons can actually be used for a tessellation? To understand this, let's look at hexagons. So if I look at hexagons, I need to be able to put them together to kind of cover the circle of 360 degrees. And I see if I put 3 of them, or almost 4 of them together, I can cover that bounds there. If I look at the interior angles of these tessellations, I can see that they're 120 degrees, which means that when I put those 3 together, I'm going to get 360, which is going to completely cover the page. So if we have 3 pentagons, that would not work because the interior angle of a pentagon is 108 degrees. And if I put 3 of them together, 108 times 3 is going to be less than 360. So we're not going to be able to surround that vertex, and that gap that's left is too small to put another shape in. On the other hand, if I tried to include that 4th one, this is the problem that I would encounter. It would have to be underneath something, and then it would not fall under a tessellation. So pentagons cannot be used for tessellations because of this reason. Here are the shapes that make a regular tessellation. If I'm looking at the regular polygon, this is going to be the measure of that interior angle that when you're putting them together, you have to make sure you can get to 360. Since 360 divided by a number greater than 120 is smaller than 3, and the number of sides of a polygon cannot be less than 3, no regular polygon with more than 6 sides can tessellate. So this is something you may have to show your students, or a fact you may have to present to them, that once we hit more than 6 sides, we cannot actually tessellate with the shape. If I want to have a semi-regular tessellation, I can have 2 different shapes with 2 different sizes and use them to complete a tessellation. If I'm tessellating with other shapes, there's only 3 regular tessellation shapes we can use: a square, an equilateral triangle, and a regular hexagon. I can look at some alternatives like the lizards, okay? So one thing that we have to make sure of is that the sum of those measures is going to equal 360 if I start trying to look at shapes outside of regular polygons. So a regular pentagon does not tessellate, but non-regular pentagons will tessellate like these shown. So you can look and see every side is not congruent here, and because of that, I'm actually able to create a tessellation. These tessellations were discovered by Marjorie Rice, and the problem of how many types of pentagons tessellate is really unsolved today. There's a lot of different ways to draw pentagons, and they are going to tessellate in many different ways. Creating tessellations utilizing translations is one way to look at it. If I have a figure and I draw any shape on the interior of that rectangle, then I cut it out, I'm going to be able to slide it, and the resulting shape will tessellate in the plane. So it's kind of like you're creating puzzle pieces where they're always going to match up and align in the plane. Another method of forming these tessellations would be taking a series of rotations where you're cutting out something out of an equilateral triangle, and then you're rotating it around that 360 degree shapes until they lock together. And this is an example of one of those where I'm able to lock them in together and to tessellate that entire plane with it.